Hello, grade 11. So, this is our module 3, quarter 4. In the next few weeks, as you accomplish all the readings and activities, you will be able to demonstrate understanding of the energy changes in chemical reactions. At the end of this learning module, you are expected to explain enthalpy of reactions, relate concepts of energy changes to practical application. For your module assessment, the Let's Prepare, at the end of this module, you are expected to solve the given problem set involving calculations of enthalpy and heats of reaction. Same with other problem sets that you have prepared. Solve the given problem set in activity 4, present in GRESA method, and include in your solution your strategy and analysis. You may use the space provided in activity 4, or you may use a separate sheet and attach it to your module. As always, practice orderliness, cleanliness, and avoid erasures. The highest possible score is still 30, but each number may not be of 10 points, but the total will be 30 points. And then for activity 1, this is review of specific heat and heat capacity calculations. I hope that the difference between specific heat and heat capacity is already clear. So I have underlined the given values. And for number 2, you have to use or you have to equate the heat of iron and heat of water. You just have to consider which has the negative sign. Then readings 1 is about enthalpy. So the concept of heat flow is usually cool objects get warmer at the expense of other objects. But scientifically, this process requires more careful examination. The conditions under which heat flow occurs will have an impact on the measurements that are made. We have two conditions to consider. This is the constant pressure and the constant volume. So in the given example, 1 mole of octane at constant volume, it can release a heat of 5.45 raised to times 10 raised to 3 kilojoules of heat, while at constant pressure, it is 5.48 times 10 raised to 3 kilojoules. If you observe, there is a small percentage difference. But in the engineering consequence in designing safety systems for large octane storage containers, it may incur a safety issue because when thousands of moles of octane burn, the difference of total energy released may be of importance for safety. Then we go to defining enthalpy. So we have two mathematical functions for energy. First is described and calculated in the previous modules, which is internal energy, which has a mathematical equation of delta E is equal to Q plus W, wherein W is equal to P delta V. This equation now allows us to see in how internal energy is related to heat. And if the volume is held constant, delta V is 0. Therefore, this variable, the P delta V, will be 0. You will now have an equation of delta E is equal to QV, which indicates a constant volume. And then another mathematical function of energy is enthalpy, which is heat flow under constant pressure. So it is defined as H is equal to E plus PV. From this equation, you can substitute or follow this derivation. You will have an equation of delta H is equal to Q minus P delta V plus delta PV. Since, as mentioned, this is under constant pressure, so there is no change in pressure, therefore there is no delta V. And also, for the sign, you will have delta H is equal to Q minus P delta V plus P delta V, which will cancel out the two variable. You will now have your equation as delta H is equal to Q subscript of P, which indicates a constant pressure. And then, for a process at constant volume, the measurable heat, so to summarize, for a process at constant volume, the measurable heat flow is equal to delta E, the change in internal energy. For a process at constant pressure, the measurable heat flow is equal to the change in enthalpy, which is delta H. Enthalpy is the more Enthalpy is more useful term because constant pressure conditions are more common in real life experiments or in real life study. So we have a term that is delta H is equal to H final minus H initial, or final enthalpy minus initial enthalpy. So when heat evolves from a system, the process is said to be exothermic. Delta H is less than 0. And in an exothermic process, the beaker, when you hold the beaker, it feels hot. And in heat is absorbed by the system, the process is said to be endothermic, which has a value of greater than 0. And the beaker in experiments will feels like or will feel cold. This is an illustration of what have been read or what have been discussed above, the endothermic versus exothermic reaction. Then for the activity 2, this is a test of understanding of what you have read. So you may reference your answer from the paragraph above. As for example, as stated in paragraph, what number of paragraph? As you observe, I have put numbers before each paragraph. So for example, this is paragraph 5, this is paragraph 4, and so on. So you may start your answer with this statement. And then, of course, there is a computation, which I think is mostly direct substitution. But please be careful with your sign convention. If heat is absorbed and if work is done by the system, or heat is lost and work done by the system. Readings 2 is about enthalpy of phase change or heat of phase change. As heat flow into a substance does not always raise its temperature. As given in this example, ice cube is at 0 degrees Celsius, and as ice melts, liquid water is still at 0 degrees Celsius. But if heat continues to flow into the resulting water, its temperature will begin to rise. For similar reasons, there will be heat flow in any phase change. So, this is an illustration of how phase changes from solid to liquid, liquid to gas, and from solid to gas, and the other way around, or its reverse reaction. So these phase changes generally take place at constant pressure. The corresponding heat flows should be viewed as changes in enthalpy. The heat required to melt a substance is the heat of fusion. And it is termed as delta H subscript FUS. So another is um, delta H of vaporization, which is a heat of vaporization, which is known as delta H VAP. So this is from liquid to gas phase change. So heat of vaporization will always be positive. And then the counterpart of heat of vaporization is the heat of condensation, which will have a negative sign. So as mentioned here, the values of enthalpy change in opposite directions have the same numeric value and differ only in their signs. So it is because the strength of the intermolecular forces varies from one substance to another. And the magnitude of the enthalpy change for any phase transition will always depend on the substance involved. So this is the value of enthalpy for water. So there is a standard table, but since water is very common in our examples, so this is the value for heat of fusion for water, freezing, vaporization, and condensation. So if you observe, fusion has a positive value while freezing has a negative value. And then vaporization, positive value, and then condensation has a negative value. So the heat will depend on the amount of substance undergoing the transition. So it will take more heat to melt a large block of ice than a small cube. So that's why we will arrive at a formula or equation that delta H is equal to N times the heat of phase change. So in this relationship, it does not include delta T. As mentioned earlier, this is at constant temperature. Phase changes occur at constant temperature. So phase change. So this is an example computation. If you are given grams, so convert it to moles. Since in our equation, we are using per we are using the value of moles. So this is an example of the strategy and your analysis. So in activity 3, let's calculate. I did not put any tip since most of these problems is direct substitution. All you have to do is find the number of moles and the value of the phase change. So this is condensation. Number 1 is condensation. And then number 2 is fusion. And then activity 4, which is your module assessment. So you may write in this space provided, or you can just solve it in a separate sheet and attach it to your module. So for questions and inquiries, clarifications, don't hesitate to message me. Thank you.